Okay, I've got a student coming in here in a minute. What are you all? That'll be fun. But anyway, I tried. I'd already started this thing. You got to. You watched me draw this. This is called an Atwood's machine. And then I got a phone call, and I forgot. Even though I've got the directions on my wall on how to pause QuickTime when I'm recording, I blew it. But this time, when he knocks, I'm going to know how to. I'm going to know how to pause this recording. All right. Anyway, this is an Atwood's machine. And the reason I bring it up is you can't go through a physics class, 210 class, without looking at the Atwood's machine. All right. There's two things we want to solve here. We want to solve for either the acceleration, we want to solve for the acceleration and the tension. Okay. It's not that hard. And I'm going to do it all in variables. Okay. It's going to be a regular physics thing. Do it all in variables. Now, there's two ways you can do this. You can look at, and you just break it into its two parts. You can look at, the first way is to break it into its two parts. Okay, so let's go ahead and break into parts. All right, so we look at mass 1. Mass 1 looks like this. The forces in mass 1, okay, the sum of the forces in the y direction are equal to, now mass 1 is accelerating this way. Mass 2 is accelerating this way. They both have the same acceleration. Notice both tensions are the same. So the sum of the forces for mass 1 is equal to m1 times a, which is equal to t minus m1g. Okay? All right, well, if I was given the two masses, I've got two unknowns and one equation. Well, that's fine. Then the tension for mass 1 is equal to m1 a. I'm assuming that mass 1 has less mass than mass 2. And so when they both feel the same force, this is going to pull with a greater force, okay, and pull it down. All right, so because they're in the same gravitational field. So is equal to m1a plus m1g. Okay, so that's what I'm done. I've found an equation for the tension. Now I'm going to look at, I'm sorry about that arrow being there. Now I'm going to look at mass 2. Okay, and mass 2 is equal to sum of the forces in the y direction are equal to m2a, but that's wrong. What's wrong with this picture? Look at acceleration. Which way is it going? Right, it's negative. It equals negative m2a, which is equal to t minus m2g. Okay? So, I wind up with m2g minus m2a is equal to the tension. Ah! Now let's combine. Combine what we know, okay, to find the acceleration. All right, so I'm going to say this t is equal to, so t then, m2g minus m2a, well that equals t, but up here I said that t was equal to m1a plus m1g, okay? So now, what am I going to do? I'm going to say, all right, let's get all the g's on one side and all the m.a.'s on the other side. So I'm going to subtract m1g from both sides. So I get m2g minus m1g. So that phrase goes away on that side. And I'm going to add m2a to both sides is equal to m1a plus m2a. So therefore, the acceleration of the thing, I'll just factor that out. Factor out my acceleration. I get m1 plus m2 is equal to m2 minus m1g. So A is equal to m2 minus m1 times g over m1 plus m2. There you go. I just divide that by both sides. Now, what about the tip? Well, I find A, and I just stick A into. So I go ahead and find A, and I've got two equations for the tension already. Once I find A, that becomes pretty simple. Now, the second way to do this is like a train. All right. So let's look at the Atwood machine as a train. In other words, we're going to take this guy and put him along the x-axis like this. Assume it's frictionless. Well, no, it's yeah. On a frictionless surface, here's M1, getting pulled by a tension this way. The string still goes through. Here's M2, getting pulled by a tension this way. This is all I've done. I've just taken this piece and flipped it up here. Like that. And this has M1G going like this. And this has M2A going this direction. Remember, the masses are known; they'd be given to me. So I look at this whole thing, which is accelerating. Oh, this is M2G. That's what's pulling that. Okay. So this whole thing is accelerating with A going that direction. So sum of the forces in the x direction this time is equal to minus M1G plus T minus T plus M2G. Well, look what goes away. This is equal to minus M1G plus M2G. Well, what does that equal? Sum of the forces in the x direction is the whole system being pulled that way, so that is equal to M1 plus M2 times A. And look what I have. Let's flip-flop these. So we've got the M2G minus M1G over M1 plus M2 equals the acceleration. Then I break it down to its single. Let's look at the tension. Let's look at block 1. Find the tension. So if I just look at block 1, it's got a tension going this way. And it's got M1G pulling it this way. Ergo, and it's got an acceleration going that way. So the sum of the forces in the x direction are equal to M1 times A, which is equal to minus M1G plus T. I've got M1A plus M1G is equal to the tension. Piece of cake, because I know what A is from here.